In the last video, we talked about the helium nucleus, which contains 2 protons and 2 neutrons. Protons and neutrons in the nucleus are called nucleons, and so I'll use that term a few times in this video. So here's a picture of the nucleus, right, with 2 protons and 2 neutrons, and we know it's stable, even though we know like charges repel, and so these 2 protons are repelling each other, and that's the electrostatic force. So let me go ahead and write that here. So the electrostatic force says like charges repel. We know that this nucleus is stable, so there must be something else holding the nucleus together, which we call the strong force. So the nuclear strong force is stronger than the electrostatic force. The strong force acts only over short distances, though, but it does act between all nucleons. For example, a proton-proton interaction is the same as a proton-neutron interaction, which is the same as a neutron-neutron interaction. And you can get into much more detail about the strong force. That's not really the point of this video. The point is that this nucleus is stable. Right, and let's think about why. We have equal numbers of protons and neutrons, and so that's interesting. And so let's think about the atomic number, right, which tells us the number of protons, which we represent by Z, and the number of neutrons we could say is capital N. And so if we're concerned with the ratio, right, the ratio of neutrons to protons, so the N to Z ratio. In this example, we have 2 protons and 2 neutrons. So 2 neutrons over 2 protons is equal to 1. So we have an N to Z ratio of 1. And it turns out that nuclei that have small numbers of protons, so if you're talking about Z is less than 20, they have stable nuclei when the N to Z ratio is equal to 1. So when N over Z is equal to 1, you can say you have a stable nucleus. So equal numbers of protons and neutrons turns out to be stable. So for this example, the helium-4 nucleus is stable. Thinking about that, let's look at carbon-14 next. So we have carbon-14. So let's get a little space right down here. So carbon-14, atomic number of 6. Therefore, carbon has 6 protons in the nucleus, right? So there are 6 protons. Number of neutrons will be 14 minus 6, so 8 neutrons. So what's the neutron to proton ratio? So what's the N to Z ratio here? Well, the N to Z ratio would be 8 neutrons and 6 protons. And obviously, that number is greater than 1. So we have an unstable nucleus. The carbon-14 nucleus is unstable. It's radioactive. It's going to undergo spontaneous decay. All right, it's going to try to get a better neutron to proton ratio. So let's look at the nuclear equation which represents the spontaneous decay of carbon-14. And so here is our nuclear equation. And when you're writing nuclear equations, you're representing only the nuclei here. So, for example, on the left side of my nuclear equation, I have carbon-14. We're talking about only the nucleus. So we're talking about 6 protons and 8 neutrons in the nucleus. And so let's look and see what happens here. So carbon-14, right, the carbon-14 nucleus is actually going to give off an electron. And so that's pretty weird, and we'll talk about more why in the next video. It's a conversion that's governed by the weak nuclear force. Right, but we know that an electron has a -1 charge, and so that's what we're talking about here, right? So here for carbon, we have 6 protons. Let me go ahead and write that, 6 protons here. An electron has a -1 charge, so let's write a -1 charge here for the electron. And the carbon-14 nucleus is turning into the nucleus for nitrogen here. So let's look at what we have. So our atomic number is 7, right? So we have 7 protons. So let's go ahead and write that here, 7 protons. And 14 minus 7 gives us 7 neutrons, right? So we look at the mass number here. So 14 minus 7 gives us 7 neutrons. And so that ratio, right, the ratio of neutrons to protons is 7 over 7, which is equal to 1. So that implies that we have a stable nucleus here. So that's the reason why carbon-14 undergoes radioactive decay. Let's look at more details about a nuclear equation, because that's really what I'm most concerned about here in this video. So the number of nucleons is conserved. So let's use a different color here. So we have 14 nucleons on the left. We have 6 protons and 8 neutrons. And on the right, we also have 14 nucleons, 7 protons and 7 neutrons. So obviously an electron is not a proton or a neutron. So nucleons are conserved. Right, so we have 14 on the left, and we have 0 plus 14 on the right. Also, charge is conserved, and so that's what we see down here. We have 6 positive charges on the left side. On the right side, we have 1 negative charge and 7 positive charges. So negative 1 and 7 give us plus 6, right? So we have plus 6. So nucleons are conserved, and charge is conserved in a nuclear equation. And notice what happened here. Right? We changed the identity. Right? We went from carbon to nitrogen because we changed the number of protons. We went from 6 protons to 7 protons. And so that's the idea of transmutation, so changing one element into another element. All right, so for nuclei with small numbers of protons, the N to Z ratio, the ideal one is 1 to 1. So for protons, so for nuclei with more protons, it turns out the ratio changes. So let's look at that. So as you increase the number of protons, the ratio changes for a stable nucleus. So the N to Z ratio turns out to be 1.5. So as you increase in Z, right? So as you go above Z is equal to 20. So as you get more and more protons, you need more neutrons, right? You need more neutrons. And let's think about why. So if I have a bigger nucleus here, so this is a very poor representation of a nucleus. I think about 2 protons. Let me use magenta here. So I have 2 protons really close to each other. All right, we know that there's a weak electrostatic repulsion here, and there's a strong nuclear force, right? There's a strong nuclear force between those protons. And the strong nuclear force wins, but this is only when you're talking about short distances. Remember, the strong force acts only over short distances. So if you have protons that are far away from each other, right? So these 2 protons here are far away from each other, there's still a repulsive force. The electrostatic force is still present, so they're still repelling each other. But you don't have the strong force anymore. And because you don't have the strong force anymore, eventually, as you keep increasing the number of protons, right, you're increasing in the electrostatic force, and you get to a point where you need more of the strong force, and so you need to add in more neutrons, right, to balance things out. So you need to add in more neutrons here, and that's the reason for this increased ratio. You need more neutrons as you increase the number of protons here. All right, so when you get beyond approximately 83, right, so let me go ahead and write this down here. So once you get an atomic number greater than 83, so bismuth, the repulsive force of the protons, right, this electrostatic repulsive force that we talked about here, is so great that pretty much all of the nuclei are unstable and will undergo radioactive decay. And so we'll talk in the next video about the types of radioactive decay that you might see.